In this episode, we're going to be talking about big O notation. We've got a question here about a couple different code snippets in Python and how they would affect big O. So we've got the first problem here is n equals 200. I just kind of arbitrarily made that. We're actually going to be passed an n value that could be different. But we're starting at I equals 100. I just used 200 for all of the n values, just so that we could kind of see what's going on. Because I think the easiest way to work with these things, if you have an unknown piece of code and you want to know what the time complexity is that you can just run it and kind of see what happens. So in this one, we've got I starting at 1. And then as long as I is less than n, we're going to keep running this while loop where we double the value of I. So let's go ahead and run this. And you can see it starts at 1, right? That's what we initialize it at. Very quickly, it becomes 2 because we're going to multiply it by 2. And then we're printing out what the current value is. So this escalates really quickly. You can see that it's exponentially increasing, right? And so because it's exponentially increasing, it's logarithmically decreasing how long it's going to take. So we're going to say that this is a log n. This is what we mean by log n, because it's not going to be n where n is 200. It's not going to take 200 steps. It's going to take some logarithmic reduction of that, right? So because it's doubling each time, we hit that maximum of 200 really quickly. So that's what a log n looks like. And problem two, it's pretty similar, except instead of starting at the bottom and working our way up, we're starting at the top. See how it says n equals 200, and then we're letting I equals n. And then what we're doing is dividing each of those I values by 2. And so when we run that, um, it ends up being pretty much the same thing. This is a little bit clunky how it has I greater than 0, because I is technically always going to be greater than 0. It's never going to quite stop. But it does stop in the sense that you see how it reaches some extremely small value. It gets smaller and smaller, and eventually it reaches a practical limit where um, we just can't divide it in half anymore. And so it's effectively 0 as far as the rounding is concerned. And so this, I would say, is also a logarithmic, so big O L log of n kind of a problem, because you can see that it's also this is not a linear uh, this is not a linear problem. So it's definitely changing logarithmically. Um, 3 is a little more tricky. So let's go ahead and run this. And you'll see the pattern. It goes 1, 2, 4, 8, 16, 32. I mean, this looks logarithmic, right? But it's logarithmic within the context of decreasing values. So we have a for loop. So for I in range 1 to n. So this is going to loop over 200 times. So this is going to be time complexity n, right? Or we say linear because it has to loop over every single value. But then that we're adding in this additional component right here where there's a while loop that is only going to trigger for values of j that are less than n. And so let's imagine what happens, and we're setting j equal to I. So let's imagine for the first 100 values, um, we go along and we do this. But what happens when I is 101? Let's imagine what happens when I is 101. So j equals I, which is 101. So now 101 is the value of j. So it says while j is less than n, 101 is less than 200. We're going to print j is the current value. So it does 101. And then it doubles that. And so we have 202. We click over to this while loop again, and 202 is not less than 200. And so it does not trigger again. So it only triggers the one time for all the values, not just 101, but 102, 103, 104. All the values from 101 up, or really 100 and up, only trigger once. And the larger values like 99, they'll trigger multiple times, but they only trigger twice, right? It's 99 and then it's 198 and then it can't fire again. So the larger that these values for I are, the closer they are to a constant time complexity. So not even logarithmic, but constant. So this is like somewhere in between n log n at the worst case scenario and just n linear time complexity, because this part constants out. Um, so it's somewhere in between those um, for its complexity. But I think you could say that it reduces to be just big O of n. You could make a case for either, that it's its worst case scenario is closer to a n log n, but I would say that this is going to be a n complexity. So big O of n. So just to kind of go back and remind ourselves what each of these were, we said that this one was log n complexity. And this one also was log n complexity. And this one is either n log n in the worst case, but more likely log n, because there's so many constants there. Like you see how it continues on. First of all, you're getting fewer and fewer of these terms each time as you go, and then by the time you're getting past 100, like it only prints one of these. You see how these later values like 196, 197, 90, they only trigger once. So the early values trigger multiple times, but a decreasing number of times, and then these trigger just once. So it gets on average more like O of n. All right, so now we've got one left. Let's take a look at problem 4. And again, I just used 200 as the time complexity there, or I mean as the n. And then, so when we're looking at the time complexity of this, it starts at 1, and while this is less than n, which 1 is less than 200, we're going to print its current value, and then we're going to raise it to the second power. So 1 raised to the second power is still 1. And then that raised to the second power is still 1, and so on and so on. So you see that this actually is going to cause an infinite loop. So its time complexity is infinite. This does not ever stop. So this is an infinite loop. All right. So I hope that although if this were like, let's say 2 or 3 or something like that, then this could actually be if it had some base other than 1, then this would be like the log of a log, because it's exponentially increasing, and so it's not multiplicatively increasing like this one did. See how it was multiplied by 2 in each time. If we had something like, let's say I is 2, let's just change this to 2, and you can see how quickly, I mean, this is like over and done with really quick, right? Because it just immediately gets astronomically larger. So 2 squared is 4, 4 squared is 16. By the time you're at 16 squared, you're already past 200. So this just goes extremely fast. This would be log n. So big O would be log of n. But that would only be if this were a base other than 1. Because it's a 1, we have an infinite loop. Okay, so hopefully that made sense, and you guys are a little bit more familiar with Big O notation. And I will see you in the next episode.